discussing autoencoders. Autoencoders is a neural network, as in two neural networks arranged in such a way, as in, so we give this is a neural network, this is a neural network. So the purple images of it is this is the neural networks. We first of all take a input images and we convert into a lower dimensional images, like this, lower dimensional space, like this, from high dimensional input to lower dimension latent space. And we this is the encoder part, which encode the data, which encode the data into a lower dimensional space. And this encoder part try to learn those and try to encode encode the input into a less dimensions which which can represent this bigger dimension images, and we call this a bottleneck, this is this part, this encoder part is role the role of is it's to encode the data into a pretty low dimensional listening. And we have this latent space, with the compressed form of the original input. And we the send this compress or less dimension input to the decoder part. Decoder part is just a neural network, another neural network, arrange in such arrange in such a way, we provide that low dimensions, and its function is to reconstruct the same images, from the small dimensions of this Latin space representation, the compressed form of the input data, we give that to the decoder part, and it try to reconstruct the original images, and so and our objective our objective is to minimize those reconstruction errors. I will just read out for use in this definition, what is it, isn't it? An autoencoder is a special type of neural networks that is trained to copy its input to its output, isn't it? As basically it is trained to copy its input to its output, isn't it? For example, given an image of handwriting disease, an autoencoders first encode the image into a low dimensional latent representations, then decode the latent representation back to an image, isn't it? It first of all encode any image. It's not a handwriting, but any images. It first encode the image into low dimensional Latin representations, and then decode the Latin representation back to images. And the autoencoders learn, the main purpose is an autoencoders learn to compress the data while minimizing the reconstruction errors. You think you can think that, we are giving the input images and we are trying to predict that same images, what's the matter of using this, but our purpose is does our purpose of using this network is to get this latent space representation of our data, latent space of the data. And our main purpose from this is to compressing, compressing the data, to compressing, compressing the data, from higher dimension to lower dimensions. If we are able to success to convert this lower dimension data to a new reconstructed image as same as the input, our objective is fulfilled, and it is also used in denoising of images. And if you have a noised image, it can be used for denoising purposes. And this is used for sparse representation, means sparsity. You can understand the sparse, the variety, the differentness, the uniqueness of the data, the sparsity of the data. We are also can get the sparse representation of the data. And the other types of autoencoders can be used in data generations like VAE and other type of variation autoencoders. But it's a simple autoencoders. We are not supposed to get we are not su- we can't get this new sample, from this, this simple, uh, deterministic. We call this as a deterministic autoencoders because we we does not include the stochastic process, or you can say that we doesn't sample. In simple word, to keep it simple, we just compress the data, into low dimension and try to reconstruct this. We does not generate data, new data as any. We will generate from variational autoencoders, but from this deterministic or simple this from this autoencoders we does not generate data as any, doesn't generate data. And why we use autoencoders as any, what's the main purpose is any? First of all, as any, if you have read the PCAs, if you have a concept of PCAs any, PCA, what does the PCA do? PCA is any convert higher dimensional data into lower dimensional data. PCA is used for dimensionality reduction. I think the unsupervised learning and autoencoders comes in the same space of dimensionality reductions and from converting higher dimensional data into lower dimensional space. But in our case, we use this in neural networks rather than those eigen operation, but we use just neural networks which is a non-linear optimization. If we have multiple layers, let if doesn't understand it's okay, just and then see and we use for data compression for example to transmit data in you have a in your mobile phone Google uses Google implant or decoder model decoder model. They first use the encoder to compress your images and they send less dimensional images via internet and your and your decoder model just reconstruct the the decoded input sent by the encoder of Google, and then you get the full reconstructed output so I think it will help to lower the mobile bandwidth, and that's it. And other advantages of using autoencoders is to train the encoder part. Once you train the encoder part by using any input data as any, first of all, I will read you that the train encoder part is used to transform the original input data into a Latin space representation. First of all, it will transform the original input data into Latin space representation, and this Latin space gives the compressed form of the original data, as in the compressed, the compact form of the original data, as in which can be used later on, and let's go to the type of autoencoders. This is a PCA, you convert multiple dimensions into single dimensions data by applying PCAs, and there are several types of PCAs, not PCA but autoencoders. We have linear autoencoders. This is a linear autoencoder system. We have only input, output, and only one. This center is an Latin space representation or low dimensional space. From this diagram, I will show that this is our original input images. This is our low dimensional representation of the input. We map map x to x with this weight as in WF as and we map this hidden to the x tilt, which is approximately equal to the x as by WG matrix, and h we obtain h by applying dot product f by mapping in WF with x input, WF with x, and this in x tilt is with mapping h dot h, we get the x tilt and saying, and we our our objective is to find these voids WF and W. Our objective is to find this void matrices and this and this is insane. And we try to first of all we multiply by this and then multiply this by this is insane. First of all we multiply by this means we first what we do, we multiply x to WF, and then we get some quantity, and from this we get some quantity, we multiply with WG is matrix, and minus xn means The original one as any, and this is the mean square error. So we apply backpropagation algorithm and minimize this objective using function. And in some mathematical notation we use, in this is a G means our decoder model, F means our encoder model. First will we compute this and we get H, and then we multiply with this is the WGC and minus the what is the target variable is. And if we not just one as in, if you implied several as in, we go to the deep autoencoders as in, guys, this deep autoencoders is in, consist of is in, several hidden layers in, as you can see is in. So what will we take the original sample and mapped it through not only one hidden layer, we implied hidden layer here is in, and H is in, this will help to capture the more complexity of the data as in, and we first of all convert X into H and then we reconstruct from H to those X tilde is in. X and X tilde are approximately same as in, but it's better to denote like this. It's in, we are approximating the same, we are reconstructing this in guys. Is in, we first of all convert this into H and we try to reconstruct as to extent this in. And then guys, this is the simple non-linearity. It will impose non-linearity. Our model is not direct because we impose by introducing hidden layers, we imply non-linearity. And denoising autoencoders means we will do the project on this. We will do the code implementation on denoising autoencoders, where it's any where we try to try to remove the noise from the noise data to get those pure data and marks autoencoder means we just remove some parts of the images and train the model to get to recover that the remove part doesn't it? And it helps to capture the interesting features some different doesn't unique features using marks or autoencoders. It can be used on somewhat transformer also is marks approaching is we remove some of the thing and we tell the model is to predict that thing. And sparse autoencoders means we see the sparse autoencoders means the variation in data and sparsity of data is we're just converting data into we're mapping x to is in z, and then we are mapping is in f2 into the s is in s, which the different s is the manifold is in, so we convert, we try to is in try to is in minimize we are trying to get the variety of data. I will show you in there here is in, this is our is in, uh, what is this is in, this is a simple as in this from year to year is in, from year to year each is our as in the original normal as in autoencoders and to as in get the sparsity of the data as in we impose this regularizer as in which which helps to as in which helps to as in get the sparsity of data as in, but in practical form it is a non-convex problem as in, so it is hard to get the closed form solution of this regularizer. So we approximate to this as in which is convex as any convex problem to get the optima as any. This is this part as in, this is same. I think this is the same loss as in we are just adding as in this regularizer part to maintain and to get the sparsity of data as any. So this is as any this term was any this term is the number of non-zero entry in the vector produced by app as in non-zero entry. This is the non-zero entry is in and z and z, and we can't evaluate this part as any which is responsible for responsibility in data as in, so we try to approximate by this, but in practice it work. In practice it work. So let's see the code implementation of the model that's in Google. Here is any continue editing is any. First of all, I will go to back to the listening. This is the Autoencoders. Uh, I'm just copied this code from here as any from TensorFlow as any, and just I have just copied and just pasted there, and you can also go from here also, but I have it copied here as any. So simple way of not doing something, pretty simple way of doing it. Just importing some necessary live. I just go through it quickly, is any just importing matplotlib, numpy, pandas, tensorflow, vr, and accuracy score, precision, recall, trend splits from layer, importing layers and losses, and we are using this data says family, fashion amnest. We are using it, and we are importing model, and just we are loading data from amnest, and this is I'm just what I'm doing here is just converting those data as 255 pixel into just this is a data scaling operation. I'm just doing scaling operation to the pixels and so I'm printing the shape as in first I'm we have around 60,000 60,000 train images and 10,000 test images and with dimension 28 cross 28 as in, and I'm defining defining the autoencoders model listening. I'm just getting a class of and passing the model listening. I'm just initializing this init method listening, which takes Latin dimension and shape. And what I'm doing here is just I'm defining this as Latin space, giving the shape of the model listening, shape of the image listening image, and this is the encoder part listening. It will first flatten the image into two-dimensional into one-dimensional, 22 plus 28 into one-dimensional vector. It will flatten this image into the Saturn layer, and then it would pass through the Latin dimensions, is then it pass through the one dense layer is of Latin dimension with activation value. This is our encoder part, is encoder part, and this is our decoder part, is the weird or dense. We are what are doing here a mat dot reduce plot as any shape activation sigmoid as any, and we are reshaping it to the original shape of the images. In possible we are converted into one dimensional in Latin space, and then as in, we are receiving it back to the original shape, and we are just defining another method without call listening call method encoded shape dot encoder of x, and we're parsing decoded to return decoded, and this is a shape. We are defining the shape as an active shape and Latin dimensions. Just we are calling the creating the instantiating the class object, compiling with the mean squared error and oh, then we're training the model listening with for 10 epochs. 10 epochs, and then just I'm doing just encoding the images and just passing to the decoder part. So numpy means just converting into dot numpy arrays. And just I am just possible I'm passing to the images to the testing. I am This is the testing part. I think this testing part we're just providing the test images into the encoder part and we're decoding it. And I'm printing this is original images. I'm just defining this fixed size. I'm giving this and I'm running the loop for 10 times and saying this is the subplot type and then subplot, and I'm printing the original images and giving a title and axis false, y axis false. I'm not declaring any axis. And same for decoded images means decoded images. This is the output of the input X test of I is in this is the X test of I is in. Then it will reconstruct it, and you can this is the original one, and see the reconstructed one is in. I think more or less Autoencoders is doing fair amount of job. Hello guys, in the section we are gonna go implementing this in autoencoders, this in image denoising. So I have imported a few libraries that I've already installed for the previous code implementation. As in just I am importing the same dataset, as in loading the same dataset, pass an mlist, and what I am doing here is just normalizing the pixel values as in pixel values, and as in just I am adding new axes to the training data sets, and then this is our shape of the data. So we have added the new axis 1 1. So and this is the noise factor noise factor of 0.2 is 0.2, and what I'm doing here is extend plus noise factor into because I am calling the random normal as random with normal method as and I'm just giving the shape as and this will add the noise factor to the all training dataset and test datasets, and just I am clipping value of clip clip value of minimum 0 and clip value maximum of 1 is I have defined here for training and testing is in noisy dataset, and just I'm printing the noise dataset is, and you can see this is original plus noise is so I have inserted the noise, and so this is a noisy dataset. We'll using this dataset and the actual data original dataset, and we'll train our model as just defining autoencoders, convolution autoencoders. So what we have, this is our encoder part, this is our encoder part, this is our decoder part, and just we have been just giving X input to the encoder, and it will give the encoded value, and we will pass it to the decoders, and we'll get the decoded value, and returning the decoded value when you call this when you call this method call method so what I'm doing here is just creating a sequential model with input shape of the images, and just downsampling images from just decreasing the dimension of images from 28 to 16 16 not 16. This is I think a convolution layer, but I'm using stride of 2 I'm using kernel and stride of 2 stride means it's a convolution operation which will downsample my images and I'm uh, next time using the convolution 2D to downsample images it is stride of 2 it will reduce 28 plus 28 into low dimension images, and I'm just defining the decoder model here and this is the 2D transpose will upscale the images from low dimension, it will make high dimension so I'm using kernel size of 3, standard 2, and activation value and padding as same, and I'm just from 18 to 16 I'm just reversing it reversing it, and I'm getting my previous my original input from here it's the last one convolution, and kernel size 3 and applying sigmoid and padding same as we are just what we're doing is just it's a reverse operation as of this as and I'm just defining the encoder and giving X and decoder to encode it and getting the decoded, and I'm just it's calling the I'm instantiating the class and compiling and fitting data has any relation, and what I am just giving the testy this data test I can also test noisy, and this will encode the images is in images, and we will pass the encoded image to the decoder, and it will give the decoded images, and we will see is And for I am just what I'm doing here is I am just noisy images. This is I'm just showing printing the noisy images in n is equal to 10, and this is the fixed size, and from range I to from 10 times it loops will run as an and the 10 images will be printed as an you can see here as an we have 10 images of noise images. And what we're doing here is just I'll show you. This is tf dot switch. We are just giving those x test noisy images. This is access noisy images from first loop runs. We are giving the zeroth index element, and we are just set false. We have just removed the axes, so the x and y axes, and we are displaying the reconstruction as any. Similarly, in similar fashion as any, we are just printing reconstructed, and we are just giving the decoded of. We give this to the encoder, and we give this to the encoder as an access noisy. We give the autoencoder as encoders, and we get the decoded images. So the ith index of noisy will be the access noisy will be the decoded, predicted by the decoder will be the decoded images. Simply we are giving access noisy to the encoder model, and we are getting decoded images. And what I'm doing here is just that as in just decoded images arise and printing and just setting false other as false plus and plot. So this is our code implementation part. The limitation of deterministic autoencoders is it does not include sampling species from a data distribution as any. So as any data distribution is a space as any space as any from where we take samples as any and give to the decoder, and decoder will generate new data as any in this space in this approach as any deterministic approach as any the data distributions we does not define any. We have data distribution, but as any we does not include the sampling processes as any. So this is not used for new data generation as any. We will discuss about it in a VAE as any where we include sampling processes as any. That's it as any. We are on those any track from autoencoders to as any autoencoders to as any VAE is any VAE based on autoencoders. Will go through that part as any. As study in a nutshell is any we have go through is any what is autoencoders, why autoencoders, types of autoencoders, and we see the code implementation and limitation of this autoencoders. So in the upcoming is any lecture we'll go about various autoencoders and understand the core ideas of various autoencoders in the next session. So that's it.